about whether evolution should be taught in schools and so forth, and the world, evolution is just a theory. Classical test theory is just a theory. Right? That we shouldn't be teaching it in schools.
Don't worry, we are.
The item response theory is just a theory too.
I know this, and this is what I was talking about. Like, I was talking about distribution error, and Megan asked a question about it. I gave it, with Megan's help or with Megan's data, gave a talk this year about things along those lines. And so I generated data where the true factors distribution looked like this. There were two categories. And boom. And when I estimated it with CFA, it spread them out. It unsquished them, right? It made them into more of a scale. Now, it's a weird looking distribution for it, and you might be able to recover them well, but you could, if you play with the parameters just right, you might get something that didn't give you the same type of overlap. So this is that last source of error, the source of error that we talked about that involved the factor distribution error. Hong Ling said, but wouldn't this last one not fit your CFA model? And here's the funny thing. I generated this 10,000 times, and the largest RMSEA I found was 0.019. So that's scary too, right? Anyway, the things that we get into when we say just a theory, we're getting into data distribution. This is where IRT shows up more as the data distribution right here. And then what do you do after that? Well, there's factor distribution. And then I'll go a step further. This is the things I could think of, and actually my wife and I could think of, put our heads together on this as much as we could. But, you know, there's likely to be things that we haven't thought of yet. And then after we think of those, there may even be more things we haven't thought of yet in there. So yes, just a theory. All right? But it sounds so serious. But anyway. So, questions before we go on. Anybody? I'm going to change my pointer options. I'm going to change it to a highlighter, I think, right here. Oh, nope, that didn't work either. Never mind. All right, so one thing I wanted to emphasize before we go on is the idea of models. And it's an interesting point that I feel like I struggle with in terms of teaching this material and so forth. So I grew up in a lot of classes that we didn't talk so much about models, or we sort of talked about models, and then some classes you get into models, like IRT, you get into models. Structural equation modeling, you get into models. And it never really saw the connection between the two. And I did this for a living. I took 5 years of quant classes and statistics classes. And what was lost on me was the model framework, that everything we do is somehow incorporated into a model, right? Those of you who do Mantel-Hansel diff testing, you hear about that? There's a model involved in that. Last time was did you guys talk about equipercentile equating? Model involved in that, right? Everything is wrapped into a model somewhere. And even if you can't see it, it usually has one tied to it as well. And so when you think about it from that light, then all of a sudden it brings about a whole set of new circumstances with it as well. So I want to use this to underscore that point, that idea that classical test theory is really part of a larger model that we can assess fit with. If you take my multivariate class, 905, next spring, I do the same thing with multivariate. I try to teach everything in a model framework. If you pick up a regular multivariate textbook, you'll see things called multivariate analysis of variance, canonical correlation, principal components analysis, and no models attached to any of those. Whereas really, if you put an overarching model involved, you can get each one of them with a specific set of constraints. So I feel like what drives me is the teaching side of my job is I'd love the disconnect between like models and not, right? When you don't do a model, you actually are doing a model, you don't realize it, with a lot of serious constraints that you probably wouldn't put in should you realize it. When in the world, when you look at like grant proposals and you look at papers that are submitted, maybe not as many papers, but you look at people who would really do this for a living, the distance between what we're teaching you in classes and what we're doing for funded science these days is just keeps growing. I'm stuck at this point. This is something where I just really feel like we should sort of change how we do our curricula to give a better chance of getting you closer to where those are. Anyway, that's how I teach. My philosophy where it comes from. So there, off the soapbox. So up to this point, we've seen a whole lot of stuff. Any questions, actually? Cool. I'm just going to ramble on. Hear Templin talk. Yeah. Yes, Julie. No, please.
If you could give me an example
Yeah.
about the difference in what we're teaching and what we do in the grants.
Absolutely. Well, the teaching part of it, I feel like what we do is teach a lot of things disconnected, and then a lot of things that are antiquated, right? So when you look at the science part of statistics and the science part of psychometrics and the science part of quantitative measures that we really get into, the science part is always 20 to 30 years ahead, but we seem like that's getting further and further along. So, like if you look at a grant, if you were to, for instance, propose a grant where you would say, okay, I have a bunch of school districts, and I want to see how something relates to achievement in each of these school districts. And in your grant proposal analysis, you may say, well, I'm going to do a regression in each one of these school districts. And someone will say, well, wait a minute, we don't do that anymore. In fact, there's why. We have error in the scores, and we're going to put it into a multi-level model that does all of it all at once. And yet, to get to, that's a fairly common problem, but to get to that in teaching, you have to take 3 or 4 years of classes to get there, and you're learning all the things that you have to unlearn once you do get there. And I think that's part of what it is. Now, some of the stuff I'm talking about is not even, I don't think, well known. I'm kind of trying to put this lecture in the part where there are some things I don't even know what. There are some questions I have about how do we determine these two last cells, and when we get into like how do we tell model fit and everything else. So there's some things that aren't, but I think we have a path that we're going down where we're going to know that, but we're not going to have people out in the world doing that. Right? And the funny thing I joke about is if to somebody who hasn't learned these things, when all you have is a test score, none of this matters. Right? If all you can just total things up, why would you do all this? All you're going to do is put yourself in a world of hurt. Why? All right? Or better yet, it'll just be the same as the test score. And the latter one is at least a little bit closer to the truth. It may be the same as the test score, but it may not be. But also, it doesn't matter. How do you evaluate whether good research is good? If your world is test score, test score, test score, test score, and then someone comes along proposing a factor model or IRT model, why would you go and say, oh yeah, that's really a neat way of treating the data? So it's an interesting interplay between quantitative science and what actually happens. Anyway, it goes beyond that actually. I'm on a riff right now. If you look at least in educational measurement, our programs are pretty steady. We don't see a lot of turnover. In quantitative psychology, which is where I have my degree, there was a continual trend since the 1960s, 70s. People closed down their quant programs. Right? I like to joke, the people in the psych department know it. They've already figured it out. They've done. I had a full professor over in the psych department here, I think I've told you the story, say to me before, listen, we want you to teach our kids, this is my brand new professor on the job, we want you to teach our kids ANOVA, because ANOVA hasn't changed in 60 years. We want psychometrics hasn't changed in 60 years. And it's like, there's just no, like, you realize that if what you learn is what you learn in grad. I felt like that is a perspective, he put it into words that were very blunt, but it's a perspective a lot of people take. Why do this? Why does it matter? So, why? Maybe I'm trying to justify my place in the world with what matters, but at the same time, it's an interesting perspective. If that's all you know is the test score, then yeah, none of this matters. You cancel out, you close down your programs, you do all this, and then you find, for instance, what we're seeing recently is that none of your research is reproducible because you find a lot of type 1, you're chasing error, chasing noise, chasing whatever else. And so I think that's, it takes years to find out. So I got to find a way to find the balance. I haven't found it teaching it yet. I'm always talking about life out of balance and everything else. My life's out of balance. But I'm pretty much always out of balance. Maybe you all know how it feels, right? Constant struggle to keep the right amount of time with everything that you want to do. But anyway, I hope that helps. Anybody? Interesting stuff. Yeah. Anyway, we haven't solved it all. We're still doing it. It's just still evolving. Anyway, let's talk about how to do secondary analyses with scores. I'm going to bring back how I introduced SEM to the class this year. Remember the first week of class, all the way back in January? Hugh was just, not even, he was negative months old. It was My life hadn't. My life is always changing, but it drastically changes when a baby comes into it. But I gave you this example from simulated data where I had 150 participants who provided self-reports of happiness, and they provided their marital status. And I said the happiness scale was roughly like a 5-point Likert scale, and marital status was whether or not you were married, yes or no. And we were interested in, ultimately we worked to a structural equation model where I said we don't need a sum score, right? We have happiness, this is our measurement model right here, and we're predicting it with marital status, and measurement model, structural equation model, and so forth. Here are all the equations that went with it, and this was the analysis itself. And what we found with the standardized estimate, this was the standardized no x, which means because the marital happiness predictor was a 0, 1, we don't need to standardize for it. We just want to standardize based on the factor itself. We found this standardized estimate to be 0.546 and not significant. 0.142 is the p-value. Remember this? Does it flash back to those days? We were all happier and whatnot. Actually, pretty happy now. I'm just tired. You know how it goes, right? Maybe you're happy. I hope you're happy. Comparing that the same analysis with the sum score, we took happiness, added the 5 items together, and just put it in a regression. Predicted it. And when we did that, we found the following. First of all, where's the model fit? There is no model fit in a regression. It's saturated. We know this term now, right? We're visiting this lecture. But if we look at the standardized estimate for this, our standardized estimate was 0.416, and the p-value was 0.008, which said people who were married have, on average, 4 standard deviations higher happiness than people who are not married, and that's significantly different from 0. Right? So now we get conflicting information. Right? The previous SEM analysis said, hey, sorry, I said 0.4. We're 0.546 standard deviations higher, but not significant in the SEM analysis. And with the sum score, we're 0.4 standard deviations higher, but it is significant. So what do you believe? Right? And so what I want to tell you is now in thinking about what we just did, we take a sum score. We took all those sources of error that we had, which in this case, the sum score I created, so I can tell you where the error happens to be. That analysis I just created for you has measurement error, but actually does not have dimensionality constraints, none of these else. None of this else. Because I generated the data. I know exactly what the data distribution were. All of that was measurement error by itself. Right? I added things up. If you go look at the file, I've got it online, it actually has decimal values for each Likert scale variable because I didn't want to go and convert them to categories. All right, so that's where the decimal values come from. I generated it from this normal distribution. You get continuous things. So I know it's measurement error, and just from that alone, that tells me that measurement error, in this case, gave me a type 1 error because in truth, when I generated these data, the true value of the effect was equal to 0. All right, so that's it right there. Measurement error of itself gives me a type 1 error. That's pretty bad, right? That's not cool. I overpowered. I thought I've got all this power in what I do. Well, let's do this analysis with the factor score, right? Again, not cool, not where I want it to go, but we have to follow the factor score thing to get where I want it to go. To do analysis with the factor score, the first thing we need to do is obtain the factor score. So we have to fit a measurement model to see that it fits. Questions on this before I begin, though? Yeah, anyway. So I fit a measurement model. I took those 5 items. I fit a happiness factor. I said it's equal tilde, which is the factor term, right? To all 5 of those variables. How's the model fit? RMSEA is 0. SMRMR is 0.024. I especially like this one. I pretty much only just want to show you the likelihood ratio test. The p-value is 0.848. Jennifer? Jennifer approves. You are the final arbiter of model fit. So, does that sound good? Arbiter of model fit. That sounds academic, right? Yeah. Anyway, so model fit, we can use the factor score. If the model didn't fit, the factor score gets model misfit error involved. So I grabbed the factor score right up. Let's see here. Where did I grab it? I did not show you the syntax where I grabbed the factor score, but I took the factor score and I put it into a model where I had the happiness factor score as predicted by the married variable. And here is what I found. We say that people who are married have a happiness that's 0.3 standard deviations higher now. So we get even lower with the number of standard deviations up. And our p-value is 0.058. I see, exactly, Kevin. What would you do with 0.058? I think most people would say publish it, right? Bridget, in your master's, did you have p-values that were significant? Awesome. You got a master's out of it. Right? I'm not critiquing your research. You have plenty of people to do that. That's not it. That is not my goal in life. But yeah, so one thing I will note, p-value is a little bit higher, but still on the low side compared to 0.14. The estimates that we see here are kind of have a trend. When we estimated with SEM, 0.546 was the number of standard deviations. When we went into the sum score, we have 0.416 in terms of standard deviations. And when we get to the factor score, it's 0.311. That shrinking is the attenuation that we're seeing. Right? Measurement error shrinks the effect. But it also makes you say that it shrinks the error that you have also. Right? I only have 150 people in my sample, which, quite frankly, if you're the one collecting the data, it's a lot. I always like to tell people, you hear about big data, you hear all this people talking about. Big data is any data you have to collect yourself. It's true, right? It takes a lot of effort and time to get 150 people sometimes. Gosh, that would take forever, right? You know how that is. Anyway, the shrinking happens. So you end up seeing a shrinking of the effect from 0.5 to 0.4 to 0.3, and that's because the error, the measurement error is attenuating the effect. You're also seeing a shrinking of the standard error, or the scale is different of it, the z value, if you will. So here are all three together. It's like I put this here. Gosh, I should just flip forward. I made these slides this weekend. You wouldn't think I'm that much different from then to now. Anyway, you see this continue to go down. The standard errors are a little bit interesting. This standard error was bigger, and now these are smaller, and that's the effect we're talking about. So this smaller standard error, this is a type 1 error, right? But a shrinking of effect, this is like what could give you a type 2 error. Remember, type 1 being you think of something that's 0 is significant and not 0, right? So marital happiness is marital status significantly predicts happiness. Type 2 error is the opposite. You don't have enough power to detect something that's really there. So we've got these competing forces, right? In the SEM literature I read to learn this stuff, I was always talked about this one being the problem, the type 2 error. It shrinks your effect. You really want to have that together, but I think what's been neglected is really it overemphasizes error. It says, oh, that error in the test score that we had, we just threw that away. It's like it didn't happen. So we shrivel up our standard errors, and we're more likely to make type 1 errors at some point, too. So it's a weird trade-off. Okay, so how do we go and take those scores and put them into secondary analyses now? Finally, we see some scores won't work because it has they have their problems, right? They are difficult to use detection of model misspecification, right? If you don't put a model in, you can't see if it doesn't fit. And then factor scores are bad because they have measurement error too, right? So pardon me. Some scores have measurement error and potentially model misspecification error. And factor scores have measurement error, although model misspecification error shouldn't happen because you should be getting your model to fit if you're doing a factor score in the first place. So what we're going to do is use factor scores for that reason as the basis. But we're not actually going to use the factor score itself. Remember we talked about the clip I showed you from the matrix from before? There is no score, right? Some of you, I understand, still haven't seen the matrix. That's okay. There is no matrix. There is no score. We want to use the distribution. We don't want to just take the summary of the distribution. We're going to use the distribution itself. And so because the factor scores have this nice distribution, and we're pretty sure that the distribution is as accurate as we can get it with the exception of switching to some other measurement model to try for a different distribution of data, we're going to use them. And what we're going to do is treat factor scores as missing data. And in a missing data analysis, we're going to do a multiple imputation of factor scores. Right? So what a multiple imputation is what we draw the part that's missing. Right? We give everybody a factor score, and then we do that multiple times. Right? So I'm going to do that 1,000 times. I'm going to create 1,000 data sets of factor scores, where each person's factor score is drawn from their factor score distribution itself. This goes by an educational measurement. This goes by another name. I'm basically saying I'm creating what's called plausible values for factor scores. And the measurement program that uses this is the NAEP, National Assessment of Educational Progress. And it's there's a paper from 1992 by Bob Mislevy, Johnson, and Meraki that really talks about the idea for it. Now, they draw 5 values. But NAEP's data, just kind of give you a sense for it. This is where I really started wising up to this a little bit. So the NAEP data, the program for NAEP, and I'm going to probably slaughter this. You can go online to find NAEP. You can Google it. AERA will pay for you to go to Washington D.C. to take a training course on it and learn about it. I did this, and the data is every 4 years we test 4th graders, 8th graders, and 12th graders. And we come up with a test that tests something like math, maybe some type of language, I don't know. And it's trying to talk about how as a nation we're doing in terms of educational progress, the nation's report card. But we do so in a way that not every school takes the test. And even then, whenever we create a test, each student takes about 40 items, which is significant, but it's not enough for the people of NAEP to think that they have enough reliability to report a person's ability estimate or their factor score. So if you do NAEP training, what you'll see is the NAEP data are publicly available. You have to make an agreement about data security and so forth, but you can get a copy of the data. And what people use it for is to compare districts or to compare states. Right? If you think about like educational achievement in different states, the ordering that you'll see every so often, it comes from NAEP usually. But the data you get, it doesn't give you 1 score per person, it gives you 5. And those 5 are plausible values. So there are different ways of incorporating those into analysis. We're going to use the methods that are essentially the same that you'd use in NAEP, which are to use these in multiple imputation. So we're going to generate multiple data sets of factor scores and then do multiple analyses. So for every data set, we're going to do a brand new analysis. And at the end of the day, we're going to pool all of our analyses together, figure out the average of the effect, the standard error of the effect, and come up with a p-value from that. Right? So essentially, we're taking measurement error and putting it back into the analysis, treating the factor score as if it was random, came from a distribution, which is what we're doing in a simultaneous analysis already. Right? So had I just done the SEM thing, all this labor wouldn't have been needed. But what we should see is if we do it the right way, we should get just about what SEM should tell us. It won't be exact. There'll be reasons for that here or there, but generally speaking, it should be close. That's the big picture. Questions? Okay. How many of you have heard multiple imputation before? Cool. On this campus, multiple imputation, I've learned, has an interesting history. What I just described to you, creating a bunch of data sets, doing a bunch of analyses. When Todd Little was here, and I'll put his name to it because he's proud of it, he pitched a method where you created multiple data sets, and instead of doing multiple analyses, you just average the data sets you created and do one analysis. Sometimes you call that a super matrix approach. That is not good. And that's not good because of what we just tried to get away from, which was all that error we're trying to sample around. When you average something, you get rid of it again. You put it back into the analysis. So he wasn't aware of this perspective. I'd say that to you in words because some of you may have advisors. I work with faculty in my department where I'm trying to steer them away from this. And I'm trying to be delicate because he was a very important person on this campus for a number of years. And so, of course, they trusted what he had to say. but there's nobody on the planet who does it that way but him. And his citations for it were in a journal where his buddies were the editors. So it's kind of an interesting thing. When he presented this at remember the esteemed circle of people I talked about last week, the 65? The first comment, I believe, was, "You can't do that." All right, so it's an interesting perspective. On campus here, he was very well respected, and so it's tough to undo the damage. I feel like we play whack-a-mole a little bit. So that's why I'm outing this. This is a Todd Little story. Sorry, Todd. Anyway, he did good things for campus in many different ways, but not that one. Okay, so these are slides from a missing data lecture. I like to put missing data into multivariate, my multivariate course. So I have a lecture on missing data because to solve it, it takes usually multivariate distributions. Multiple imputation can happen for more than one thing, and that's where multivariate normal comes in. So this is some slides from that lecture. As we talked about up to this point, dealing with missing data is important as what you choose to deal with it can really affect your results. So if you think about it, that true score of a person that you substitute a sum score in for is your version of multiple. It's a single imputed score, right? It's like I have this trait I'm after. It has measurement error to it, but I'm going to go take someone's test score, and that's just going to be their trait itself, right? That's one value, right? And it can dramatically change what you see about your results. We just saw a little bit of that from a simple simulation. Now, this is a point that was not fully realized when we started doing psychometrics quantitatively over 100 years ago. And in fact, I don't know that it was really well realized until at least Donald Rubin's work in the 1970s, but more recently, just a couple, 10, 15 years ago. So this is one of those places where thinking has changed. Pedagogy has to change afterwards. Our teaching has to change afterwards, and that's what I'm trying to do to teach differently. So I say this section has a bunch of methods that people do. There's a great book by Craig Enders, Applied Missing Data Analysis. It's fantastic. It talks about all sorts of things, statistics, but missing data is the big part of it. If you ever have a chance to read it, please do. It's fantastic. Oddly enough, it says don't ever do what Todd said to do, and Todd's the editor of the book series for it. So it's kind of an odd, interesting play on things. Anyway, so what we would think of, if we think of the factor score as being missing, then using a factor score, right, the factor itself or the true score, if we use the factor score, if we use the sum score as our value in an analysis, we've just done a single imputation, right? And single imputation is very bad, right? It's easy. You can plug it in. The problem is everything's biased. Type 1 error issues, right? So if you're look at this from a missing data perspective, anybody who does that, it's like, whoa, that's really bad. You're going to go and take your p-values and shrink them and not in a good way. They're not going to give you accurate results. I have a slide that says why it's bad science. Don't do it. You're going to make wrong conclusions about your data. Multiple imputation is a better method to do it. You are filling in your data with plausible values. I actually use that term plausible value back in the missing data lecture because I look at it as this education. We have it all case in educational measurement, but also in psychometrics. Latent variables are missing data. All right, so we get multiple data sets. After we get the multiple data sets, we need to do multiple analyses for them, and then we need to pool those analyses. The missing data, where we get them from, come from our distributional assumptions. In places where we have multivariate normal models and multivariate normal data, i.e. CFA, it's actually really easy to do compared to the alternative. It's not easy to do. I was talking about Sunday, I need a variance. That's not easy. But compared to what it would be like if we had some distribution that wasn't normal, at least there's an answer. Let's put it that way. But not easy in the big picture. Relatively speaking, it's easy. So we're going to use, in CFA, we know what the distribution of our factor score is, right? We know the mean of it. It's got that ugly product of all those matrices. We know the variance of it. We know it's normal. So for each person, they have their own mean because the factor score is different. Depends on what their item responses are. They have the same variance. We draw we use that normal distribution to draw random values from to create their new data. So here are the steps. By the way, any questions? Please stop me. On a roll. No questions. So anyway, imputation, we do the imputation part, which is we generate M for imputation. The letter M for imputation. Sorry, it's terrible. I know. The writing part, reading, writing, arithmetic, the writing R is really bad for me. Anyway, if we have M data sets, I'm going to take 1,000 this time. We just want enough to get around the variability. The smaller the variability, the less data we need. But because it's an R, I can just put extra digits on it to generate it. In NAEP, we have 5 data sets, for instance, and here we have 1,000. NAEP was also started when the analysis method started was in the late 1980s, when computers weren't as easy as they are now. So anyway, we get 1,000 data sets here, and again, for each person, we're drawing from their factor score distribution. All right, we draw from a normal distribution. Mean of it is their factor score, mean. Variance of it is the variance of the factor score. We have 150 people. That means we have 150 factor scores we draw. We do that 1,000 times. So we have 1,000 150 person data sets where we have a factor score for each person. We have their marital status also. So we put those together. 2 variables, 150 people, 1,000 times deep. The analysis then gets conducted on all thousands of those. And believe it or not, that is pretty terrible, right? We have to kind of do a loop. What's awesome is, and this is where I'm kind of confused, because Todd pitched this super matrix thing, but some of Todd's students created a package called SEM tools that actually allows you to do this correct way with Levon. So he was advising students that weren't telling people what he was doing. So there's something going on here. Anyway, I'm going to use the package created by some of your contemporaries. I think they've since moved on in other places. They were here in the stretch of time that I wasn't. So I did not overlap with them perfectly, almost. Anyway. And then finally, the pooling section is where we take those 1,000 results and combine them. It's not as easy as just averaging everything. We have to look at the variability within an analysis for each parameter versus between. And we have to come up with a combination of that to give us an accurate standard error. Those combinations are sometimes called Rubin's rules. I'm not going to go into them deeply here because this package that was created does it for you. So we just have to create the data sets. It will do the labor for us. It'll run the Levon 1,000 times. It'll take 1,000 results and pull them together. And it'll give us a result that looks like Levon output. Thank you. I mean that people don't recognize that I'm teaching. Oh my goodness. I believe in the templano-centric view of the universe. No, it's around my class, factor scores. Anyway. All right, so the key to this is distributions, and the nice thing about CFA is we have a distribution built in. If we didn't have CFA, by the way, couldn't do this, and what we'd have to switch to is something a little bit better or different. Get to that in just a bit. But here are our distribution. Remember this slide from last time? On the left is a normal distribution. This is the factor score. And to summarize it, we'd say, take the mean or the maximum. If we didn't have it normal, we couldn't just draw from it. The distribution itself is harder to draw from. We'd have to use some type of Bayesian or Markov chain to sample from it to get to it. That is what I wanted to show you, but then M+ didn't cooperate and other things didn't cooperate. So I was like, you know what, I'm just going to show you, imagine everything's normal. If you want to do this in your research a little bit later on, I can give you things to make it work. And the next time I teach this, dang it, I'm going to have this built in where we're going to be able to do this based on the software and make it easy, rather than have to make it the Wild West where you have to create your own variants for everything that you do. So the idea behind multiple imputation is don't summarize, right? If we were to take one number that was a mean or was a maximum, we weren't doing any disservice because there's all sorts of things that are equally likely or close to equally likely that could happen. Bless you. So, and this is one of those neat things. Anytime you do this, anytime you take a summary of something with error and you use it somewhere else, this happens. It's not just psychometrics. It's not just this class. It's, you know, in you may have done multiple imputation on your data, right? This method for your data does the same type of idea. It doesn't give you one value for what your data happens to be. It says what are the whole range of values that might be, and then let's sample from them, because that's the only way we keep error in our analysis for it. So, okay, we're going to predict happiness. The preliminary information is we need the mean and the variance that's there. It's ugly, but here, take a look. Here's the slide that I used to get it. This is me on Sunday. Oh, dang it, I need a variance. So I saved all those matrices, lambda, theta. What Lavon has is a function called inspect, and it provides all the terms that go into these matrices themselves. And so what I call lambda and psi and everything, they have different names for, but that's the combination. I saved all of them. I'm able to take it. I run an analysis. I'm able to extract that part I need. I then can make my factor score mean and my factor score variance itself from all of that. One little neat part of this, if you have missing data for a person for a factor score, their factor score is cool with that. Just like in maximum likelihood, missing data is cool. What happens is their vector of responses is smaller, and their mean vector gets smaller. So the thing that's missing is omitted from all these matrices in the corresponding spot. We still give them their distribution for it. So it's just skipped. We still give them a value for it, and believe it or not, that's way cooler because it assumes that value is missing at random, which means it's related to the other things in the model, which is kind of neat. Anyway. So, with that information, I drew 1,000 data sets. And this is my step for it. 1,000 data sets, my number of observations was equal to the size of the data, so 150 people. I saved everything into a list, which is something that the people who created this Lavon imputation SEM tools function needed. So, it's value for that. And I wanted to create, I saved one person's imputation string to kind of show you how it's working when I'm done. So I copied over the old data set. From that, I created a factor score itself. I drew a random normal 0, 1, and transformed it into what the mean factor score value for that person should be. Times, and this right here adjusts the mean, and this part right here adjusts the variance of the distribution. I then saved it as a variable in my new data set, and I saved the data set to my list, and I saved the first person's observation just to show a plot of it. Here is a plot of the first person's observation. Right? At the top, this is imputation number from imputation 1 to imputation 1,000. And this is drawing from that posterior distribution of their factor score. That's drawing from this function R norm, random normal. That's their posterior distribution. At the bottom here, the red dashed line is what the true distribution should look like. That's using a mean and a variance from what we can predict in our function. The dashed red line is that. The black line is what we observed through this 1,000-time imputation. It's like taking it, making a histogram, a smoothed histogram. So it looks pretty spot on, right? It's pretty cool. In Bayesian statistics, this would be called Gibbs sampling. Right? If you're doing a Markov chain, some of you might be taking Billy's Bayesian. I needed 3 B's there. Billy's best Bayesian class next year. Billy's beautiful Bayesian class. I'm going to have another B. Badass Bayesian class. I like it. You may hear about Gibbs sampling. This is Gibbs sampling, which is I have a chain of values drawn from a posterior distribution. And it's possible in this case because the posterior distribution has a fairly unique form. I could figure out its mean, its variance, and its actual distribution itself. So, in the pooling phase, back up here. the analysis itself gets done, and then I do the pooling. The standard errors come from, we have to figure out the variation of standard errors within versus between. Anyway, let me back up a second. How it works is the following. Once I have all that data, I run the following step. The multiple imputation analysis is from a function called runMI, and that's in the package SEM tools. If you're looking for it online, it's lowercase SEM capital T, lowercase ools. If you don't look with that combination, it's not going to give it to you. So that runs, this thing right here runs 1,000 analyses, and this reports the results. And take a look. The results get reported just like a regular Levon report. Looks like your output. The analysis itself, by the way, let me back up. What does the analysis look like? It is using, it treats the factor score that was imputed as an observed variable. Right? It's not a latent variable. It's a number that's imputed. So why we're treating it as observed is because that's our best guess for that one step, of the one sample of the imputed values. Right? So it's like, oh yeah, we gave a person a score, but we gave them one that's with error. And if we do this thousands of times, that should even out. Or we do this hundreds of times, up to 1,000. You following me? For the most part? Cool. So what are the results? What's the one we're looking for? The standardized effect for it gives us even smaller standard error. Sorry, smaller standardized effect, which is somewhat odd, but this is part of the deal. We get error and the number. We only did 1,000. We could have kept doing this over and over and over again. But our p-value is 0.139, and if we put that into a comparison, right here, this is pretty close in terms of p-value to making the same decision that we saw before. But still, we end up seeing our effect itself keeps shrinking. Smaller and smaller and smaller and smaller. So that's it in a nutshell. How do you want to use a score in analysis? Impute it. Treat it as random, or as missing and random, and put the error back into it. And what this analysis did with the factor score imputation is right here, we got rid of that measurement error and put it back. But that said, we still have sampling error. What? We only had 150 people. No, I know, right? That's terrible. That's part of the reason why our effect was so small. How do we get rid of sampling error? Well, let's, I'm going to go through each one of these rows in this table in this next section of the lecture and try to talk about what causes the error, what can be done to fix it, and what are the ramifications on your analysis if you leave it. Because this took a lot of work, and quite frankly, you know, if it weren't for that SEM tools runMI thing, I'd still probably be doing it, right? So it's not like it's realistic to do all of this yet. It will be coming up, dang it. 2 more years. I have 2 years till I teach this class again. By then, yeah, right. Anyway, we'll see. All right, let's take a break for 10 minutes. I know I'm a little bit early, a minute or two, but then we'll come back and I'll talk about each of the sources of error. Okay?